Let us discuss few more details of the Hemicube method. This method is available from the method list in the view factor and clustering dialog box. It is shown here. It is preferred for large complex models with few obstructing surfaces between the radiating surfaces. The basis for Hemicube method are aliasing, visibility and proximity. The Hemicube method uses a differential area method and calculates the view factor on a row by row basis. The view factor calculated from the differential areas are summed up to provide the view factors for the whole surface. This method originated from the use of radiosity approach in the field of computer graphics. It is recommended that we use the Hemicube method for large complex models with few obstructing surfaces between the radiating surfaces. The Hemicube method is based upon three assumptions. Those are aliasing, visibility and proximity. Let us first see aliasing. The true projection of each visible face onto the Hemicube can be accurately accounted for by using finite resolution Hemicube. If the faces are projected onto the Hemicube, because of the finite resolution of the Hemicube, the projected area and resulting view factor may be overestimated. This can be controlled by increasing the value of the resolution of the Hemicube in the parameters dialog box. This is where we input the control parameter for aliasing. Second basis is the visibility. The visibility between any two faces does not change. In some cases, the face I has a complete view of the face K from its centroid, but some other face J occludes much of the face K from the face I. In such a case, the Hemicube method will always overestimate the view factor between face I and the face K, since it is calculated from the centroid of the face I. This error can be reduced by subdividing face I into smaller subfaces. We can specify the subfaces by entering a value of subdivisions in the parameters group box. But we cannot do this in cluster to cluster basis option. This is the subdivisions box or subdivisions input. Next is proximity. Let us imagine a scenario where the distance between faces is greater compared to the effective diameters of the faces. The proximity assumption is violated whenever faces are close together in comparison to their effective diameters. Usually, the distance between faces is greater compared to the effective diameter of the faces. The proximity assumption is violated whenever faces are close together in comparison to their effective diameter or are adjacent to one another. In such cases, the distance between the centroid of one face and all the points on the other face vary greatly. Since the view factor dependence on distance is non-linear, the result is a poor estimate of the view factor. For controlling this, we set the limit for normalized separation distance in the parameters dialog box, which is shown here. Next problem with the Hemicube method is the blocking surfaces. If there are no obstructions between surface pairs under consideration, then they are referred to as non-blocking surfaces. If there is another surface blocking the view between the surfaces under consideration, then they are referred to as blocking surfaces. Blocking will change the view factor between surface pair and require additional checks to compute the correct value of view factor. For cases with blocking surfaces, select blocking from the surface list in the view factors and clustering dialog box. For cases with non-blocking surfaces, you can choose either blocking or non-blocking without affecting the accuracy. However, it is better to choose non-blocking for such cases as well, as it takes lesser time to compute. So for blocking, we need to select either blocking or non-blocking if there exist blocking surfaces. It is not necessary to select all surface or boundaries for calculating view factor. Depending upon situation, we can control specifying boundary zone participation. There are two ways we can specify participation of walls and inlets as well as exit boundaries in view factor calculation. One of the two ways is to use the participates in the view factor calculation option in the radiation tab of the boundary condition dialog box. The other method is to use the participating boundary zone dialog box as shown in this figure, which is accessed by clicking the select button next to the zones participating in the view factor calculation label in the view factor and clustering dialog box, which is the radiation panel. To compute view factor in your ANSYS FLUENT session, you must first set the parameters for the view factor calculation in the view factor and clustering dialog box and click OK to save them. When you have set the view factor and surface cluster parameters, click Compute Write Read button in the view factor and clustering group box of the radiation model dialog box. A select file dialog box will open, prompting you the name of the file in which ANSYS FLUENT should save the surface cluster information and the view factors. After you have specified the file name, ANSYS FLUENT will write the surface cluster information to the file. ANSYS FLUENT will use the surface cluster information to compute the view factors. Save the view factor to the same file and then automatically read the view factors. To compute view factor outside ANSYS FLUENT, you must first save the surface cluster information and view factor parameters to a file. File write surface cluster option can be used for this. ANSYS FLUENT will open the view factor and clustering dialog box where you will set the view factor and surface cluster parameters. When you click OK in the view factor and clustering dialog box, a select file dialog box will open, prompting you for the name of the file in which ANSYS FLUENT should save the surface cluster information and view factor parameters to the file. What if we have to read view factors into ANSYS FLUENT? If the view factors for your problem have already been computed either inside or outside of ANSYS FLUENT and saved to a file, you can read them into ANSYS FLUENT as well to just start the radiation calculations. To read in the view factors, click Read Existing File button in the view factors and clustering group box of the radiation model dialog box. A select file dialog box will open where you can specify the name of the file containing the view factor. You can also manually specify the view factors file using File Read View Factor menu item. Now comes the last model, that is DO model. This is named as Discrete Ordinates model. This model solves the radiation transport equation for a finite number of discretized solid angles. This is very similar to solving CFD variables on a finite volume grid. The radiation transport equation is written on a control volume of existing mesh and solved with a finite volume method, unlike the ray tracing method used in DTRM. So a finite volume equation is solved for radiation intensity like this. That is why this is considered to be a highly accurate method for radiation modeling, as it is very similar to actually solving transport equations similar to flow and energy equation. Similar to the finite volume grid which we generate for any CFD model, for DO model an angular discretization is done. For 2D this is done in each quadrant, and for 3D it is done in each octant. And n theta by n phi discrete ordinates are created, which is like a angular grid rather than a structural either 3D or 2D grid. We can control the density of this angular discretization as well, similar to the way we control density of any mesh. When you select the discrete ordinates model, the radiation model dialog box will expand to show inputs for angular discretization. In this section, you will set the parameters for angular discretization and pixelation. Theta divisions and phi divisions will define the number of control angles used to discretize each octant of the angular space. So you have to enter the number of theta divisions and phi divisions here, which is known as controlling the angular discretization. Again, similar to the P1 model, the basic assumption for the DO model is gray radiation. If we want to solve real radiation cases which are non-gray radiation, we have to similarly define wavelength bands and wavelength range. If you want to model non-gray radiation using the DO model, you can specify the number of bands under the non-gray model in the expanded radiation dialog box. When a non-zero number of band is specified, the radiation model dialog box will expand once again to show the wavelength interval. You can specify a name for each interval as well as start and end wavelength of band in meters. Note that the wavelength bands are specified for vacuum. ANSYS FLUENT will automatically account for the refractive index in setting band limits for medium with different from unity. So for non-gray radiation, we have to input the number of bands similar to the P1 model input as well as the wavelength range here.